All right, let's power through this real quick, why don't we? Now, this first one, number one, this first problem has a fairly unpleasant setup in that, I mean, just look at those experiments. Whoever designed this experiment ought to be shot. But it is possible to find a couple of different runs to work with to try and make this not quite so horrifically awful. So, for example, let's go ahead and do run 5, or experiment number 5, and experiment number 1. Just look at those two on there. And what you'll see is that experiment number 5, oops, that's not going to do it. Well, I can't do a quick highlight on here, so we'll just won't. Experiments 5 and 1, the concentration of hydroxide stays the same, but it triples for chlorate. So let's go ahead and hop on over and do some math. Okay. So, experiment 5 and experiment 1. So it's going to be log over log, and each of our ratios, or each of our logs, will be a ratio. It's going to be rates over concentrations. So, run 5 and run 1. 0.06 for run 1, 0.02 for run 5. That's our concentrations. And our rates, 0255 and 00268. So we go ahead and plug that into a calculator. That gets us 2.05. Don't be too worried about things like this. That's pretty much just rounding errors. What we're looking at here is an exponential factor of 2. So it's chlorate, sorry, not chlorate, just chlorine dioxide raised to the second power for our rate law. We can do pretty much the same thing to find the exponential for hydroxide, except we're going to have to pick different experiments. Okay, let's go ahead and do experiment 4 and experiment 2, because definitely not experiments 4 and 2. We'll want experiments 4 and 1. That would work quite nicely. And what we see there is chlorine dioxide. It's 0.06, 0.06. Stays the same either way. The concentration of hydroxide, 0.03 to 0.06, it doubles. And we look at the rates, 0.0255, 0.2492. It's going to be a little bit less than 1. So we're going to go ahead and say it's 1. But just to show you the math real quick. And that is equal to 0.948. And that rounds to 1. So now what we have of our rate law is rate is equal to K times chlorine dioxide raised to the second power, hydroxide raised to the first. We still need to find K, though. That's super important. Van, river, etc. So what we need to do is we pick one of our experiments. It might as well be experiment 1. There's no reason for it to be anything in particular. And we plug it in for that particular experiment. So experiment 1, 0.06, 0.03, 0.0255. In the math coming up, I do the math correctly, but I accidentally use 0.06 instead of 0.03 for the concentration of hydroxide. So that means that the answer I get for K is going to be off by a factor of 2. It's going to be half as big as it should be. It should be 236, I believe. So our rate, 0.0255, is equal to K times 0.06 squared times 0.06 to the first. We just solve for k. 0.0255 over 0.06 to the third. Why not? Plug that into our calculator. That gets us k is equal to roughly 118. So that gets us the full rate law. And this really is the answer you're looking for number 1. So let's move on to number 2. Oh, well, fill in the blanks. Unfortunately, they don't give you a word bank, but, you know, that's not vital. If the rate of a reaction is second order with respect to the concentration of reactant A, then the graph of A versus time, nope. It's second order, so it's going to be 1 over A versus time. We'll produce a straight line. Second order is 1 over A. First order is natural log of A. Zero order is concentration. What we're looking for is the graph of 1 over the concentration of A. The molecularity of a reactant in the slowest elementary step of a reaction mechanism shows the blank of the reactant in the reaction rate law. That's the exponent, is what they're looking for there. The molecularity of a reactant, that is to say, the coefficient, gives you the exponent, or the order of the reactant. So I would accept either one, personally, but, some tests, they don't give you that option. A substance that speeds up a reaction but overall is not consumed is called a catalyst. Enzyme would not be sufficient. You want to go with catalyst on that one. The oxidation state of oxygen in the compound hydrogen peroxide, H2O2, is -1. If you get that wrong, I will laugh at you. Okay. Now, E, F, G, H, and I are all not relevant to our needs here. Those are all for Unit 3. So let's move on. All right, number 3 is kind of confusing. And it's unfortunate that it involves an exothermic reaction. That's more from Unit 3, but we can get quite a bit out of here. Okay, so there's a slow step, 2 fast steps. It's 3 elementary steps. And therefore, what are we looking at here? So what they're looking for is a reaction progress or reaction coordinate. It's not a real thing so much, but it's a useful tool. Okay, so we start with reactants, and we're going to end up at products. It's an exothermic reaction, so let's go ahead and make that clear. Exothermic means that it is releasing energy. Oops, not reactants for that second one, just products. All right, so it happens in 3 steps. Let's go step 1, step 2, and step 3. Okay, it doesn't have to be quite that discrete. They don't all have to be endothermic like that, but they could be. Or not endothermic, exothermic. But they could be. And here we have an intermediate, and here we have another intermediate. So here we see it asks for the activation energy for the slowest step, and that is step 2. So that would be right here. EA for step 2. That would be A. They're also asking for a chemical intermediate. So, let's see, this is A. These would both be B. Okay, so the energy change of the reaction, boom. This is C. The products, oops. So this would be E, and this would be D. All right, so that's the sort of thing they're looking for there. If you want, you can try and make yours prettier than mine. Okay, now for this one, this is a nice little Hess's Law problem. Oh, wait, that's also Unit 3. That's not going to be on the test. Calculate the time taken, in number 5, calculate the time taken for the decomposition of a radioactive isotope to be 80% completed if it follows first-order kinetics and has a half-life of 2.84 hours. All right, 80%, half-life 2.84 hours, first-order kinetics. So first-order kinetics means that the natural log of the concentration at time t is equal to the natural log of the concentration at time 0 minus kT. Now they gave us a half-life of 2.84 hours. So half-life is equal to 0.693 over K. So K is equal to 0.693 over T1/2 is equal to 0.693 over 2.84 is 0.244. So that's what we're going to plug into that equation when we get to the time. All right, so what we're looking for is 80% instead of 50%. So natural log of a t minus a sub t minus natural log of a sub 0 is equal to negative kt. Then, thanks to the magic of math, or the magic of logarithms, that gives us a sub t over a sub 0 all inside one logarithm. Sorry about the noise, that's my cat playing with the cat door. Is equal to negative kt. Now, they asked us for 80%. They asked us for 80% completed, so we have 20% left. So that means that a t over a naught is only 0.20. We don't actually need numbers there. 80% completed means there's 20% left. So how long will it take? T equals negative natural log of 0.20 over k. And when we plug those numbers in, hopefully we get a positive number. We do indeed. We get 6.60 hours. All right. Generally speaking, that's how you can solve that sort of problem. How long does it take for something to happen? Sometimes they give you the starting and final concentrations or amounts or what have you. That's not always necessary. If they give you a fraction, like they did here, or a percentage, then you can just plug that in as the ratio of your two concentrations. And that is just as good a way to do it. If you can find a way to rearrange your equation to get that. That's not always easy or doable. But for a first order reaction, it definitely is. All right, balancing an equation using the half reaction method. The nitrogen hexoxide plus bromide yields nitrite and bromate. So we have a reaction to balance. We have N2O4 plus Br minus goes to NO2 minus plus BrO3 minus. So negative 2 times 4 is negative 8. 2 nitrogens plus negative 8 equals 0. 2 nitrogen equals positive 8. Nitrogen equals positive 4. Bromine equals negative 1. 2 times 2 is negative 4. Nitrogen plus negative 4 equals negative 1. Nitrogen equals positive 3. 2 times 3 is negative 6. Bromine plus negative 6 equals negative 1. Bromine equals positive 5. So 4 to 3 is reduction. Negative 1 to 5 is oxidation. So let's go ahead and split those up into our half reactions. Oxidation, this bromide goes to bromate. Reduction is into O4 goes to NO2, 1 minus. Balance everything but oxygen and hydrogen, so we need 2 of those. Now we balance oxygen by adding water. We need 3 water up here. We don't need any water down below. Now we're going to need to balance hydrogen, so we need 6 hydrogen up top. No hydrogen to balance down in reduction. Now we balance charge, so -1, 0, -1, and 6 means we need 6 electrons here. And now we're going to need 2 electrons down here, which means we need to multiply this by 3, so 3, 6, 6. Now let's go ahead and cancel. Okay, so the electrons disappear, and that's it. All right, so now it is 3 dinitrogen tetroxide plus bromide plus water, 3 water, yields 6 nitrite plus bromate plus 6H plus. Now, it's out on the first page, this is taking place in a basic solution. So we need to get rid of those H plus, so 6OH minus on the right, and plus 6OH minus on the left. All right, H plus and OH minus makes water. So the water disappears on the left, and we're left with 3 water on the right. So the final answer is 3 N2O4 plus bromide plus 6OH minus yields 6 NO2 minus plus bromate plus 3H2O. Now, just to be sure, let's go ahead and double check all of our elements and our charges and our everything. So, can we reduce the coefficients? No, we have 3, 1, 6, 6, 1, 3. There's nothing we can divide those by to make those smaller. So we check our elements. We have 3 times 2 is 6 nitrogen on the left. We have 6 times 1 is 6 nitrogen on the right. Bromine, 1 and 1. Hydrogen, 6, and 3 times 2 is 6. Now oxygen, 3 times 4 is 12, 6 times 1 is 6. So 12 plus 6 is 18. And on the right, we have 6 times 2 is 12, plus 3 is 18. So all of our elements check out here. As for charge, we have 0, -1, -6, makes -7 on the left. And then we have -7 over here on the right. So everything checks out. This is your answer for number 5. Or number 6. Whatever. Oh, what is the oxidizing agent in this reaction? The oxidizing agent is the one that is reduced. The one that's reduced was dinitrogen tetroxide. Okay, reaction mechanism. Is this reaction mechanism feasible? Let's see. No, it is not. It is not balanced. Okay, we have 2 chlorine atoms in this first reaction on the right-hand side, so that's monatomic chlorine. And on the left, you notice we have 2 chlorine atoms in the second reaction, and 1 chlorine atom in the third reaction. So that alone is enough to make this not work, because you end up with 1 chlorine atom on the left. So that is not a feasible mechanism. All right. And if the first elementary reaction in this proposed mechanism is the slowest reaction, propose a general form of the rate law. Oh, okay. Another reason why this mechanism isn't feasible is because you have a tetramolecular, that's kind of ridiculous, a tetramolecular reaction in the second step. So that's just garbage. Yeah, all told, this mechanism is, whoever designed it should be ashamed of themselves. Dragged out in the street and beaten with a hose. Okay, so if the first reaction in the mechanism is the slowest, propose a general form of the rate law, which is consistent. Well, that would just be rate. That would just be rate equals K Cl2. Because it's an elementary reaction, so the rate law for an elementary reaction is just very simple, with the order being equal to the coefficient of the reactant. So that's all she wrote. Number 8, thermodynamic data. Nope, that is not part of this test. Number 9, also not part of this test. That's also enthalpy. Let's scroll down. Oh, there is no. Okay, that's it. All right, so we have powered our way through that practice test. Okay, hope that helps.